Subscribe now.
Before we go on with the tutorials, I'd like us to talk about some special properties of digital Fourier transforms. And these properties are some properties that can be used to solve some questions concerning digital Fourier or discrete Fourier transforms. So let's go ahead and look at these properties. The first one I want us to look at is the linearity property. For the linearity property, assuming that DFT of this time domain sequence is equal to, let's say x1 equal to x1 of k, and also DFT of x2, which is another signal sequence, is equal to x2 of t, x2 of k, then we can say that the DFT of ax1 of n plus bx2 of n is equal to ax1 of k plus bx2 of k. So as you can see, this is self-explanatory, right? Whilst b and then a are the coefficients of the sequence in frequency domain and then time domain as well. So let's look at the second property, which is also the periodicity property. For the periodicity property, we made the case that if x of k is some endpoint DFT with a finite duration sequence that is maybe x of n, then we can say that if we have x of n plus n is equal to x of n for all real numbers or for all values of n. That is, if you have n and you add this duration to it, you are supposed to still get this duration. And if you're able to get it, that's why we say it's the signal is periodic, right? Or the sequence is periodic. Looking at the second one is also if x of k in the frequency domain, we add this period to it, the results that we are going to get is still going to give us x of k for all values of what k. So this is also something about the periodicity property that we can use in solving digital Fourier transforms. For the third one, the property 3 is a time reversal. Time reversal property. So for the time reversal property, that one also states that if the DFT of x of n is equal to x of k, then we can say that the DFT of maybe x into bracket l minus n, which is the number of sequence or the length of the sequence of the length of the sequence, is equal to x into bracket l minus k. Yes. And also the second one in time domain, if DFT is equal to x into brackets n minus n, then we can see that this n minus n is equal to x of n minus k. So let's take note of these ones. Let's look at some different sets of properties as well, and we will come and use this property to solve some examples after we are done discussing them. So the different set of property, which is property 4, is the circular time shift. The circular time shift property. So for the circular time shift property, it states that if the d of t, right, if the d of t of x of n is equal to x of k, as we already know, then we can say that our d of t of x into brackets L. Let's say, okay, let me do it this way. Let me use this variable instead. Into bracket n minus n naught. It's equal to x of k multiplying by exponent negative j 2 pi k n naught over n. Looking at this was made possible because inside here we have n minus n naught, and therefore n is equal to n naught. So instead of kn over here, we replace the n by n naught. That's why you see n naught over there. And let's look at the circular frequencies. What is the circular time shift? And then the next one I want us to talk about is the circular frequency shift. For the circular frequency shift property, it also states that if our df of t is x of n is equal to x of k, as we know already, then we can conclude that the DFT of x of what n multiply by the exponent of j 2 pi over n l n is equal to x k minus l. This means that if you get something like x k plus l, it means that we are going to get x of n multiplying by negative j 2 pi l n over n. Right. The same thing applies to the circular time shift. If you get x of n plus n naught instead, we are going to get x of k exponent j 2 pi k naught over n. So let's take note of it. So basically, we are moving forward to different set of properties as well. We will come and solve some examples using these properties. So now, the next property that we want to talk about is the circular convolution property. That we have discussed is the circular convolution property. For the circular convolution property, it states that if DFT of x of n is equal to x of k, then we can conclude that our DFT of x of n convolve to x2 of n is equal to x1 of k multiplied by x2 of k. There's a popular statement for this that convolution in time domain is equal to multiplication in frequency domain, and this is what it means. So when you get two sequences which is being convolved in time domain, in frequency domain we multiply them. That's one thing that we need to take note of. Let's look at the multiplication property. For the multiplication property, it also states that if DFT of x1 of n is equal to x1 of k, and the DFT of x2 of n is equal to x2 of k, then we can conclude that the DFT of x1 of n multiplied by x2 of n is equal to 1 over n, and then x1 of k, then convolve to x2 of k. So this is kind of a reverse of the circular convolution property, and the only difference is that here we divide by and then we convolve in the frequency domain. So convolution in time domain is multiplication in frequency domain, and then multiplication in time domain is a 1 over n multiplied by convolution in frequency domain. So these are properties. So let's move to the next set of properties. The other set of property of which we have already been using. One of them is the complex conjugate property. So during my previous tutorial, I made you understand, I made you to know that, or I informed you that, or I discussed the fact that if you are doing a 4-point DFT and you find the second element and then the first element and then the third element, you can actually find the last element by taking the complex conjugate. So now the complex conjugate is a property we have been using already. And this state that if DFT of x of n is equal to x of k, then DFT of x conjugate is equal to x conjugate into bracket 1 L minus k n, which is also equivalent to x conv of n minus 1. So for autocorrelation, which is the energy aspect, that one I think we will use it. You can also write it as Rxx of k to be equal to x of k, x asterisk of k, which is the complex conjugate, and can also give it to us as x of k all squared. And the last one I want us to discuss is the Parseval's theorem. And this theorem states that if DFT of x of n or x1 of n is equal to x1 of t, and DFT of x2 of n is equal to x2 of k. Now, the theorem states that the summation of n equal to 0, and then n minus 1, x1 of n, and then multiply by the x2 conjugate of n equal to 1 over n summation of k equal to 0, n minus 1, x1 of k, and then multiply by x2 of conjugate of k. So this is basically the theorems that I wanted, or the properties that I wanted us to discuss. You can read more on this, but before that, I'll end here and then see you in my next tutorial.